Hello, I'm Dennis Morris. I'm a mathematician and a theoretical physicist. In this video, I'm going to derive the Dirac equation in the same way that we believe Dirac derived it in 1928. The Dirac equation is an equation that describes the electron as an electron field. In certain circumstances, it describes the neutrino as a neutrino field. The Dirac equation was presented to the world in 1928 by Paul Adrian Maurice Dirac. It is seen as a cornerstone of modern particle physics. Although the Dirac equation is revered by particle physicists, as we shall see, it is mathematical nonsense. In a video subsequent to this one, I will derive the Quaternion Dirac equation, a mathematically sound equation that describes the electron as an electron field. The Quaternion Dirac equation is an equation that leads to a non-chiral electron field and to a chiral, that's left-handed, neutrino field. It is a recent development. The Quaternion Dirac equation is very similar to electroweak theory. But before we look at the Quaternion Dirac equation, it is easier to rederive the Dirac equation in the way that Dirac did it. So in this video we are deriving the original Dirac equation. There are four equations in particle physics. There is the Schrodinger equation, there is the Pauli-Schrodinger equation, there is the Klein-Gordon equation, and there is the Dirac equation. We will look at all four of these equations in this video. All four of these equations are derived in a similar way. We begin with an energy-momentum relation. We insert the quantum mechanical derivative operators for energy and momentum. And we then insert a field for the operators to act upon. There are two energy-momentum relations in physics. There is the classical energy-momentum relation, and there is the relativistic energy-momentum relation. Note that, as is common practice, we have set the velocity of light to unity. The correct energy-momentum relation is the relativistic relation, but the classical energy-momentum relation is approximately correct. The Schrodinger equation and the Pauli-Schrodinger equation are based upon the classical energy-momentum relation. The Dirac equation and the Klein-Gordon equation are based upon the relativistic energy-momentum relation. These are the quantum mechanical operators for energy and for momentum. Notice that these are differential operators. Strictly speaking, these differential operators exist in only the two-dimensional complex number algebra. To reiterate, we begin with the energy-momentum relation. We insert the energy and momentum quantum mechanical differential operators into that relation. We then insert a field into that relation for the operators to act upon. And that's it. That's all we have to do. We will begin with the Schrodinger equation. The Schrodinger equation is based upon the classical energy-momentum relation. We take the classical energy-momentum relation and we substitute into this relation the quantum mechanical energy operator and the quantum mechanical momentum operator. In that one simple step, we have almost got the Schrodinger equation. However, we need a field for these operators to act upon. What kind of field ought we to choose? The differential operators exist within the complex numbers. Schrodinger chose a single complex number as the field. This is the famous Schrodinger equation. This complex number varies from point to point in our four-dimensional time, and so it is a function of the space and time coordinates. It is most often taken to be a function of time and one spatial coordinate, but this can easily be generalized to three spatial coordinates. This is the time-dependent Schrodinger equation. If we make the field a single complex number, independent of time, we get the standing waves which are associated with electron orbit. We take the field phi to be the electron field. According to Schrodinger, the electron field is a single complex number which varies from point to point in our space-time. Let me recap. We began with the classical energy-momentum relation. We inserted the quantum mechanical operators for energy and momentum into this relation. We then chose the field to be a single complex number that varies from point to point over our space-time. We inserted this field into the energy-momentum relation for the operators to act upon. And that's it. We have the Schrodinger equation. According to Schrodinger, the electron field is a single complex number field which varies from point to point over our four-dimensional space-time. What we have just done, we will repeat 3 more times, but we will change the field that we insert into the energy-momentum relation. On 2 of these 3 times, we will use the relativistic energy-momentum relation rather than the classical energy-momentum relation. The differences are in the fields that we insert and in which energy-momentum relation we start with. A single complex number has 2 independent variables. 2 independent variables are insufficient to describe a field with spin. Clearly, the electron is something more than a complex number. So what is it? Pauli took the electron field to be an ordered pair of complex numbers. This is enough independent variables to accommodate the electron spin. To Schrodinger, the electron field is a single complex number. To Pauli, the electron field is an ordered pair of complex numbers. All Pauli did was to change the field in the Schrodinger equation from a single complex number into an ordered pair of complex numbers. To make this equation work, Pauli had to introduce three 2 by 2 matrices, which are today known as the Pauli matrices. Great! We now have an electron field that has spin. However, to do the job properly, we ought to have started with the relativistic energy-momentum relation rather than the classical energy-momentum relation. Guess what we're going to do next? You guessed wrongly. We're going to have a little aside. There are two ways to view an ordered pair of complex numbers. One way is to see the pair of complex numbers as a position vector in a two-dimensional complex space. The other way is to see that an ordered pair of complex numbers is really a quaternion. Personally, I do not believe in complex spaces. I think they are an invention of humankind that does not really exist. We will begin with the relativistic energy-momentum relation, and into this we will substitute the quantum mechanical differential operators for energy and for momentum. This is the equation we get. It is traditional to move all the differentials over to the left-hand side. But what is the field? If we take the field to be a single complex number, then we have a field without spin, a zero spin field. If we take the field to be a single complex number that varies from point to point in our four-dimensional space-time, then this is the Klein-Gordon equation. The Klein-Gordon equation is taken to describe particles that have zero spin. Well, now we have derived 3 of the 4 equations of particle physics. There's only one left. It's time for the Dirac equation. Within the theory of relativity, time is treated as a dimension just as much as space is a dimension. These two types of dimensions have equal rights, and they should appear equally in any relativistic equation. If we are to have a single derivative of a time dimension, we should have a single derivative of the space dimension. If we are to have double derivatives of the time dimension, we should have double derivatives of the space dimensions. We have double derivatives of both time and space in the Klein-Gordon equation. What we really want is an equation with single derivatives of both time and space. The relativistic energy-momentum relation has the energy squared. We really want an expression for the energy. We need a square root of the right-hand side. When we put the quantum mechanical energy and the momentum operators into the root, we will get single derivative. People familiar with quaternions will be able to write the square root down immediately. But Dirac did not go this way. Dirac sought the square root in a far more convoluted way. As we wander, with no map and no light to see ahead, down the path of trying to understand the universe, we often wander from that path into brambles and marshland. The faster we wander down that path, the faster we wander into the brambles and marshland, the more entangled we become. I think Dirac not going down the quaternion route was a diversion from that path into a great many brambles and a great deal of marshland. Dirac began with the relativistic energy-momentum relation. He then assumed that the root of the right-hand side would be of the form shown. The alphas and the beta are objects to be calculated. We will do that calculation. We expand the right-hand side. We have used subscript variables to keep the expression short. We need this to be equal to the right-hand side of the relativistic energy-momentum relation. These can be equal if we can find mathematical objects, alphas and beta, such that the conditions at the bottom of the screen are satisfied. What kind of objects satisfy these conditions? We see immediately that the alphas and the beta are non-commutative. We note that the non-commutivity is in the sign of the product. We have 4 square roots of plus unity which are non-commutative. Clearly, the non-commutative alphas and beta are not real numbers. Nor can these non-commutative objects be two-dimensional complex numbers. To Dirac, the non-commutivity within the sign is reminiscent of a Clifford algebra. In fact, these are elements of a 16-dimensional Clifford algebra. These relations will not fit into an 8-dimensional Clifford algebra. If beta is not a real number, then there is a problem with Dirac's initial assumption. Mass is a real number. Ignoring the fact that energy is also a real number, Dirac multiplied throughout by beta. Because beta squared is unity, mass is now a real number. We have multiplied together some of the elements of a 16-dimensional Clifford algebra. Multiplying together elements of a Clifford algebra gives other elements of the Clifford algebra. Dirac introduced new names. It is these relations which cannot be accommodated within an 8-dimensional Clifford algebra. How do you write the elements of a 16-dimensional Clifford algebra? You write them as 16 by 16 matrices. But they can't be written as 4 by 4 matrices. Dirac chose to write them as 4 by 4 matrices. These are the famous gamma matrices of the Dirac equation. These matrices can be written in a different basis, of course. So what does the root of the relativistic energy-momentum relation look like now? This is what it looks like. We know what to do next. We substitute the quantum mechanical energy operator and the quantum mechanical momentum operator into this root of the relativistic energy-momentum relation. Putting the quantum mechanical operators for energy and for momentum into the root of this relativistic energy-momentum relation gives this. We then give the operators a field to act upon. This is the Dirac equation. On the bottom line, we have written the Dirac equation in the traditional form using concise notation. This is the famous Dirac equation. The mu stands for either t or x or y or z and indicates a sum of these 4 terms, as is the Einstein convention. But what is the nature of the field? The gamma matrices are 4 by 4 matrices. Dirac reasoned that the field must be a 4-component vector. We saw earlier that an electron field with spin is an ordered pair of complex numbers. 4 ordered real numbers do not have the same relations within the complex numbers, and so 4 real numbers will not work. Dirac felt himself to be compelled to make the field 4 ordered complex numbers paired together to make 2 electrons. This ordered pair of ordered pairs of complex numbers is called a Dirac spinor. It is sometimes called a bispinor. A Dirac bispinor represents 2 electron fields. Dirac interpreted this to predict the existence of antimatter. Well, that's it. We have derived the 4 equations of particle physics. But there's something not quite right. In spite of the Dirac equation being held in great reverence by particle physicists, it's a mathematical mess. The gamma matrices are 16-dimensional objects, and they ought to be written as 16 by 16 matrices. The Dirac bispinor is an 8-dimensional object, and ought to be written as an 8 by 8 matrix. The I is an element of the 2-dimensional complex numbers. It's a 2 by 2 matrix. We have 16 by 16 matrices multiplied by 8 by 8 matrices multiplied by 2 by 2 matrices. It's a complete mathematical nonsense. The Dirac bispinor is not an algebraic object. It looks like a vector in a complex space in which we have complex numbers on each axis, but two of those spaces are distinct in some way. Even fairy stories do not have such objects in them. The quantum mechanical differential operators are commutative operators from within the commutative two-dimensional complex numbers. The Dirac equation is a non-commutative equation. We ought to have used non-commutative differential operators. The gamma matrices have allegedly the commuter operation, but the gamma matrices are elements of a 16-dimensional Clifford algebra. The 16-dimensional Clifford algebras do not support the commuter operation. It is supported by 4-dimensional Clifford algebras and by 8-dimensional Clifford algebras, but no 16-dimensional Clifford algebra supports the commutator operation. Sorry Dirac, it's 0 out of 10 for this nonsensical equation. It gets worse. The gamma matrices are such that by changing the basis we can write them as matrices that have entirely imaginary elements. If we do this, all the i's disappear from the Dirac equation. The Dirac equation then is a real equation with only real solutions. What we have done by changing the basis in which the gamma matrices are written, we have changed the electron field from an ordered pair of complex numbers to a single real number. By changing a basis, we've changed the nature of the universe. That's not right. Edouard Majorana did exactly this in 1937. It sparked almost a century of debate about the nature of the neutrino. By the way, the Dirac equation is taken to describe the neutrino field when the mass is 0. I wonder what happened to the electric charge. Well, it's very bad manners, and indeed quite dangerous, to tell a particle physicist that the Dirac equation is a complete pile of nonsense, unless you have something with which to replace the Dirac equation. As early as 1929, the physicist Cornelius Lanczos, a close friend of Einstein's, proposed that the Dirac bispinor was really a pair of quaternions, and that the electron field was a quaternion field. Lanczos was ignored, but his equation still exists, of course. It's called the Lanczos equation. We won't be looking at it. In the next video, we will be proposing a replacement for the Dirac equation. The next video will see the electron field to be a quaternion field. We will call this the Quaternion Dirac equation. That's in the next video. I hope you will go on to view the Quaternion Dirac equation video. But before that, please allow me to advertise a few of my books. Thank you for your attention.